proposition. Let I belonging to lambda be orthonormal set in Hilbert space H if X is in vector in H, then the set S is equal to collection of all those EI such that modulus, in the case of complex, if F is C, if it is R, its absolute value, X with EI or you can just remove the modulus also. We are just treating this. We'll just look at this case. Collection of those EI in a product is non-zero. Okay. So S is collection of all those EIs. So from this orthonormal set, whose inner product with this X. So if you take any X, you fix it, and then take inner product with every vectors of this thing. If that is non-zero, then such a EI would be what is contained in the S. So those EIs with every vector, if you take the inner product is non-zero, then the set is either empty or countable. So here, this is what we are trying to show. So what is lambda? So lambda is an indexing set. Indexing set. So it's all orthonormal. So this is sum. So it's a sum set, which is an orthonormal. That is, every vector here is of unit norm, and inner product of any two distinct vectors over here is 0. So from this indexing set, these EIs are there. Each of these EI are what in H, of course. So S is what collection of those EIs from here. So that what happens is that inner product with every X is what non-zero. Only those EIs are here. So S is clearly a subset of this thing. Okay. So another thing is that by countable, what do we mean? By countable, we can have a finite countability. Let's say finite countability or infinite countability. That is cardinality of n, and this is finite countability. This is a finite set. So maybe some n belonging to natural number. So that is what we are saying, is that the size, or this is either empty. S is containing no elements. So let's try to prove this fact. Proof. For each positive integer n, consider the following set. Sn. It's a collection of all those EI such that absolute value of inner product of X with EI, okay, the inner product over here, the whole square is strictly greater than norm of X square divided by n. So here the n is coming into picture. Let's try properly. Let move left. N. So x is any vector in H. First observation, Sn is a subset of S for all n belonging to natural numbers. Okay. Because this object is the modulus if it is complex number, if the field F is C, R or C. If it is R, then this is what? This is nothing but if it is R or C, this is absolute value. Okay, and S is nothing but union of Sn, n going from 1 to infinity. Why this is the case? S is those EIs such that in a product of x with EI is non-zero. So if you take the absolute value or the modulus, it would be what? Strictly greater than 0, because absolute value is a non-negative real number in both the cases. So it should be n is, as n is becoming large and large, this value is becoming small and small and closer to what? 0. So this is what we observe, that S is union of this Sn. So the point is that if we know the size of this thing, Sn, we can say something about the size of S. Exactly if it is what, so our claim is the following. Sn cannot contain more than n minus 1 elements. Okay. The point is that why is it so? So what is Bessel's inequality? The Bessel's inequality says that if you have any finite orthonormal set, let's say maybe we'll use E1, E2, again abuse of notation, any, or rather not some, any orthonormal set of size n belongs to natural number, then for any x, so n is finite, and for any x what do we have is that summation mode x with ei, if you take the square, this is bounded by norm of x square, I going from 1 to n. Okay, so this is a n size finite orthonormal set. So we'll use this fact. The point is that we'll look at any n orthonormal set from the Hilbert space, and we'll try to look at this thing. Now what is Sn? Each of this inner product of x with ei is what? So Sn as a set is collection of those ei, so that absolute value of x with ei, this is what x with ei is strictly greater than norm of x square divided by n. Okay. So you have this thing. So if you take suppose, so let's say Sn has n elements. So what would happen? This is x square. So x square divided by n. Let's take n times summation of this thing. These are suppose n terms. This summation is clearly n times norm of x square divided by n. Now each of this term is smaller than this thing. This is strictly smaller than summation mod of inner product of x with ei. Suppose I have n number of terms over here. For sake of simplicity, I write them e1, e2, en. Okay, any n terms for that sake. Any n numbers are there. Maybe there may be some other indexing. I is here from lambda. I have just taken any n. So ei and so e1 rather e2, en. Some that lambda. Now this is strictly smaller. Okay, that is the definition of S. So what I get is that norm of x square is strictly smaller than this n term. So I have this set e1, e2, en. This is n size, so finite n size, orthonormal set. Okay, this would be strictly smaller than what then? Bessel inequality, what I had just written, strictly smaller than x with a whole square. So this is from here. This would be bounded by norm of x square. So what I am getting from here there is strict inequality and this is the strict. So this implies that norm of x square is strictly smaller than norm of x square for all x belonging to a, and this is a contradiction. So assuming n, if you assume more than n terms, we would have the sum of the type n plus 1 by n, which is what? This number is strictly bigger than n. So you cannot have, Sn cannot have n terms also, it cannot have more than n plus 1, n plus 2, it cannot have. So at the most, you have an upper bound. So, let's write that. So cardinality of Sn is less than equal to what? N minus 1, which is a finite. It could be 0 also. At the most, it could be n minus 1. So S, since we have shown S is union of Sn, this implies that we'll use the fact that countable union of countable. So finite is also a countable set. Countable union, this is union over countable. So countable sets is countable. So if each of the Sn is empty, then S is of course empty. If one of them is non-empty, then at the most it could be countable. So S is a countably set. So either it is a finite or infinite countable set. Okay. So that is what we have got. That finishes this part. We will use this fact in another. So some note. What do you mean by absolutely convergent series? We have seen that. What we have seen is that so the summation. So if you look at so convergence, maybe say to A and summation mod of A I going from 1 to limit rather as n tends to infinity. As n tends to infinity, norm of AI converges to, maybe say, it converges to the norm of A. So what does this mean is that this summation, this tends to 0. What does this means? Of course, this is happening, this is an object in n is a normed linear space, this is also in n. This is happening in the field. This is, so if the series converges absolutely, then it converges in the norm also. What does this mean is that norm of, so here it would be absolute value rather, because this is just a real number. So what do we have is that absolute value, this tends to 0. This tends to 0. Okay. This is absolute convergence. We have seen the proposition also. Absolute convergence implies convergence. Not only that, but the series obtained rearranging the terms also converges, and all such series have the same sum. So we can rearrange the term in the absolutely convergent series. If every absolutely summable series is summable, then it's a Banach space. That is a criterion easy to prove that. So n was non-linear, n is a Banach space. If and only if every absolutely summable series is summable. So since we are focusing on Banach spaces, so n we're talking about the Banach space. If it is a Banach space, then what we are saying is that every absolutely summable series is summable. Okay. And conversely, if every absolutely summable is summable, that is, this is summable in the field, and this is summable in the non-length linear space n, then n is Banach. And if n is Banach, then any absolutely summable series is there, then the original series is also what? Summable. So let's say there is a proposition or rather theorem. Say theorem. Bessel's inequality, okay, or the generalized. So suppose if EI is any orthonormal set, then we have what? In H. The point is that this is I belonging to lambda. So lambda is an indexing set over here. So we'll say then the summation I belonging to lambda x with EI in a product and its absolute value, if it is the field, is this thing. This is what? Bounded by norm of x square for every vector x in H. Okay, this is what we want to prove. Now let's look at some observation. Lambda, this, if it is either it is empty, lambda is finite, or lambda is countable. If it is finite or empty, we don't have the problem with respect to description of this thing. If it is countably infinite, then the point is that what does this term is there, and then rearrangement is also an issue. Rearrangement of the terms of the series. So since we have just written lambda here, they are any order. So for empty set, this sum is 0. 0 is of course bounded. 0 is always greater than norm of any x. So it's square also. Lambda is finite, then rearrangement is no issue. If lambda is uncountable, that would not be the case. We'll try to prove here, as the case is in the previous case, is that the set S, which is what collection of those x ei such that in the product of x with ei is non-zero, that is countable in nature. Okay. So lambda at most can be countable, so we have to look at this case. This is the most important part of this thing, to look at rearrangement. So the set S is collection of all those ei such that inner product of x with ei is non-zero. S is either empty or countable. So if S is equal to empty, our lambda set is just an empty set. There is nothing in that case. There is no sum. So we can define this sum as the zero sum, or this summation I belonging to lambda x with ei, this as the zero. If lambda is finite, then what do we have? If lambda is finite, then we look at suppose lambda has n terms only. This is e1, e2, en. Any rearrangement would be what? The summation of x with ei whole square would be less than norm of x square. Not only this thing for this one particular order, but all possible rearrangements also. So if S is countable, S is countably infinite, then our lambda set is countably infinite. This summation would be of this type I going from 1 to infinity. Okay. And we need to consider all possible rearrangements. Now, if you look at this series, one particular rearrangement, if we order on lambda z, if you look at this series, this series is what this is absolutely. So by previous observation, any series obtained by rearrangement have the same sum. So rearrangement is taken care of. Observe that for the Bessel inequality finite case, so this is whatever the sum is there, it's an extended real number, but the point is that from here, if you take any x with a, this is bounded by norm of x square. N, 1, 2, 3 and so on, each bounded by norm of x square. X is a H, any, H is a Hilbert space. Then this clearly implies that this summation for all possible rearrangements also of this series, this is bounded by norm of x square. Take the limit, the right hand side is independent of that. That proves this part generalized basis.